Hi, today we're looking at the notes for section 5.4, Sum and Difference Identities. So we're adding some more identities to what we've been working with. So we're beyond just the fundamental identities. On this note sheet, I have it written a couple of different ways. So this is listing all 6 sum and difference identities out. This side has them more condensed. So like this statement represents both sign A plus B and sign A minus B. So sometimes this is a little easier to learn. Sometimes people just like to learn them individually, and either one is fine. So how you use this side is this is sign A, and if you do the top sign plus B, then when you get over here, you use the top sign from this side. If you use the bottom sign from this side, then you use the bottom sign for this side. So when we get over here, if we use the top sign, which is plus A plus B, then over here we would use the minus because it's the top sign here when we connect these two together. And then if you use the minus sign on this side, then you would use the plus sign on this side because that's the bottom sign. So same thing is true here, but you have on the top, if you use the A plus B, you're going to do a plus on the top and a minus on the bottom. If you use the minus over here, then you're going to do a minus on the top and a plus on the bottom. So if you don't like the double signs written like that, then think about it in terms of this. But these are all on the back side of your identity sheet. So a couple of things I want to remind you. Sum and difference identities can be used to find exact values of trig functions involving sums or differences of special angles. So we're using the special right triangles. Hipparchus, which I probably just said his name wrong, but he's a Greek philosopher, astronomer, geographer, mathematician. He was born in about 160 BC, and he is credited with the invention of trigonometry as well as having known to derive the sum and difference identities. So that's where they come from, just in case you were curious. Things to watch out for, answers should be exact and left in simplified radical form. Only use calculators if you are specifically asked to approximate and not an exact form. Be careful when you're doing your radical operations. So remember, when you add two radicals together, you can't add the radicand, that's the number inside, and get 6. These are two separate things. If you're multiplying and they have the same index, so if this is a square root and a square root, I can multiply what's underneath, which is 10. It's a little different if this is like a square root and a cubed root. So you have to go back to your rules that we learned. If you're doing radical 3 times radical 4, they're both square roots, so we can multiply what's underneath, but then don't forget you have to simplify this. 12 is 4 times 3. The square root of 4 is 2. The square root of 3 stays put because it doesn't have a pair to come out from underneath the sign. And then the last one I wanted to remind you about is when you have something like this, I always get students that try to say, oh, well, that's 6 and 3 simplify, and then I'm just left with square root of 2. That's a big no-no. You can't divide into a radical like that. And then we're going to work through these examples, again, without a calculator. So away we go. The first one and second problem, we're going to use the sum and difference identities to simplify the problem. So here's, I kind of walked you through this one. And so here's what we have going on. So if you're trying to find cosine of 75 degrees, pay attention that it's in degrees because you're going to want to work in degrees. If it's in radians, you're going to want to work in radians. So you're asking yourself, what two special angles add or subtract to equal 75 degrees? So the pair that I found was 30 degrees plus 45 degrees gives me 75 degrees. These have to be special angles on our unit circle, and we're doing it in degrees. Now we would think, okay, which rule or identity should we use? Well, if I'm saying this plus this, and my problem is cosine, then the identity I'm using is the cosine because that comes from the problem, and the addition one because that comes from here. So then I would go back to my list, and I would look for the rule that was cosine A plus B, because remember that plus sign is right there. So here's the rule. I would recommend while you're getting started here to write the rule down as you do your work. You're less likely to make mistakes. As you get more comfortable with them, you probably can add things in as you go, and it's not a big deal. So now that I have the rule down that I want to use, I know I'm going to call this A and this one B. So this is A and this is B. And so now I have cosine A, cosine B, sine A, sine B, and the minus is in between. Then this is where we spent so much time learning those rules from the unit circle, so you should be able to say, okay, I know cosine of 30 degrees is root 3 over 2. Cosine of 45 degrees is root 2 over 2. Sine of 30 degrees is 1/2. Sine of 40 degrees is root 2 over 2. Simplifying in here, when you're multiplying fractions, these have the same index, so you can multiply them together and get root 6. 2 times 2 is 4. Then you have your minus connecting the two pieces, and then again, 1 times anything is just itself. 2 times 2 is 4. So what I have when I put my fractions together as a single fraction, since they have a common denominator, is root 6 minus root 2 over 4. And remember, your answers have to be exact, so this is where you stop. You do not go to your calculator and give me a decimal. All right, so that's the first one. And I kind of wrote everything out as I did these first two, so you had some points of reference. All right, so let's look at number 2. So, as we're working number 2, this one is pi over 12, so it tells you in radians. You know that you're going to use the sum and difference rule with sine. So what two special angles add or subtract to equal pi over 12? So I did pi over 3 minus pi over 4 because I thought, in like terms, I thought, okay, well, if the denominators are 12, then this was going to be 4 on top, this was going to be 3, and when I subtract them, I get the minus there. So that gives me 1 pi on top and 12, which is the common denominator on bottom. Now, which rule should we use? Well, sine from the problem, subtraction, because that's the two angles that I found right here. And so then I wrote down the sine minus A minus B, and there's my rule. And then I plug my information in. A is going to be pi over 3, B is going to be pi over 4. Please pay special attention to where you put angles when you're dealing with a subtraction, because we know from all of our years of math that subtraction is not commutative, so you have to make sure you're doing it in the right order. All right, so away we go. If A is pi over 3, B is pi over 4, then sine of pi over 3, cosine pi over 4, minus cosine pi over 3, sine pi over 4, just using that rule. Now I have to write down what I know. So sine of pi over 3 is root 3 over 2, cosine of pi over 4 is root 2 over 2, cosine of pi over 3 is 1/2, sine of pi over 4 is root 2 over 2. So you're doing your order of operations, so you're taking care of the multiplication first and then subtracting in the end. So root 3 times root 2 can be multiplied together because they're both square roots, and you get square root of 6, which doesn't simplify. And then 2 times 2 is 4 on the bottom. Then you have 1 times square root of 2, which is square root of 2. 2 times 2 is 4 on the bottom, and you're subtracting, so there's my single fraction that represents those two parts. Okay, so 1 and 2 were kind of the same type of problem, and I did one with degree and one with radians for you. Now we're going to move on to the rest of the problems, which each one is just a different kind of problem. So on 3, it says find the exact value of sine 42 degrees cosine 12 degrees minus cosine 42 degrees sine 12 degrees without a calculator. And yes, you can do this without a calculator, okay, because you're going to use those rules. All right, so the first thing I want to ask myself is what identity follows the pattern. So in other words, remember this is the right-hand side of the identity. So we're looking at sine of one angle, cosine of another, minus cosine of that same first angle right here, and sine of that second angle right there. So you're looking for this pattern. So when I look at my patterns, I get this one, right? Because this would be the same angle as this, so I've got the A and the A. This would be the same angle as this, so I've got the B and the B, and the minus in between. Which means if I work backwards, that's the sine of A minus B rule. So now I know that this is A, which was 42, and this was B, which was 12 degrees. So I can work backwards because this is the side that was in my problem. All of this was given. I worked backwards to get my A and my B. So now I know that sine of 30 is what I'm looking for, and because I know sine of 30 for my unit circle is 1/2, 1/2 is my final answer. So this is where having that good strong knowledge of that unit circle that we've been trying to give you and let you build all year is really going to come into play. All right, the next one, show cosine of theta minus 3 pi over 2 equals negative sine theta. Showing is another way of saying proving, so you have to use your form. And I'm hoping after the last test we finally have that figured out, so we know we're going to write this down as our first step. We're going to pick a side, and the side that has the most stuff is this. So that's going to be what goes right under here. So here's my original identity. and then I write down the side I'm working from and I put an equal sign. This form is not negotiable. If you don't use it, you will lose the points because you're not doing an actual proof correctly if you're not using the correct form. We should be very proficient with this after the last test. All right, so here I am, and I'm looking at the rule that says cosine of A minus B, and then I can apply the rule here. So when I apply the rule, it's cosine of A, cosine of B, plus sine of A, sine of B. Now, I don't know what cosine of theta is, so that's still cosine of theta. I do know that cosine of 3 pi over 2 is 0, so I can replace that. I don't know what sine of theta is, so I still have a sine of theta. And I know that sine of 3 pi over 2 is negative 1. So when I clean this up, remember it's a proof, so you have to show it. So this times 0 gives me 0. This times negative 1 gives me negative sine theta. And then 0 plus negative sine theta gives me negative sine theta. So use the correct form. Make sure you are doing what we practiced and learned to do on the last unit, because we'll be doing that the rest of the year off and on. All right, so hopefully that proof is getting better and easier as you're getting more comfortable with the forms and the identities. You have to be able to know those identities to know which one to use. All right. Problem 5 is given 195 degrees, equals 225 degrees plus, minus 30 degrees. So it's giving you the 2 units to use off your unit circle point. It wants us to find sine 195 degrees, cosine 195 degrees, and tan 195 degrees using the sum and difference formulas. So since this is a minus, then we're going to use sine A minus B, cosine A minus B, tangent A minus B. That's what this part is telling you, and it tells you which ones to use. So we're basically going to say this is our A and this is our B. And away we go on the first one. So I'm finding sine of 195 degrees, and that is going to be sine of 225 minus 30 degrees. Don't forget your degree symbols. Then we're plugging that information into the identity. So the identity for this one was sine 225 cosine 30 minus cosine 225 sine 30. So this is A, B, A, B. So now, from our unit circle, we should be able to get the values. Sine of 225 degrees is negative root 2 over 2. Cosine of 30 degrees is root 3 over 2. Minus, cosine of 225 is negative root 2 over 2. And sine of 30 is 1/2. So remember, be careful what quadrant you're in. Whether the cosine or sine value is negative or positive will drastically affect your answer. So once I start cleaning this up, I get root 2 times root 3, which is root 6, and it's negative. And that's 2 times 2, which is 4. And over here I get root 2 times 1, which is root 2, and it's negative. And then I have 2 times 2 is 4, but we have a double negative here. So a negative times a negative makes a positive connector. Once I have that, I'm putting it together. So technically, if you just wrote it like this, that would be good. If you don't like the negative hanging out in front, you could have moved it to the back on the top and said root 2 minus root 6 over 4. That's up to you. I would take it either way. Okay, now let's do cosine of 195 degrees. So we're doing cosine of 225 degrees minus 30 degrees. So then we're going to put it in our rule because this is A and this is B. So cosine A, cosine B, plus sine A, sine B. So that's just applying our rule, and then we evaluate it. We use the numbers that we know are true, which means cosine of 225 degrees is negative root 2 over 2, cosine of 30 degrees is root 3 over 2, sine of 225 degrees is negative root 2 over 2, and sine of 30 degrees is 1/2. So when I put this together, root 2 times root 3 is root 6, and it's negative over 4. Root 2 times 1 is root 2, and it's negative over 4. And then you got to put these together in a single fraction. So there are a couple of ways you could have left your answer. You could have just said minus root 6 minus root 2. Have no problem with you leaving your answer like that because that's just one place. If you take it further, you might make a mistake as long as it's over 4. But you could have also factored the negative out from the top and put it in front of the fraction. And now on top it becomes root 6 plus root 2 over 4. So if you did this, that's great, but it's not necessary. Leaving it right here is perfectly acceptable. Wrapping up the question 5, we're continuing here. Tangent of 195, and again we're doing subtraction, so it's tangent of 225 degrees minus 30 degrees. Now in this problem we have a lot of radicals, we have a lot of fractions with radicals, so there is a little more to getting this one finished than you might think. So let's talk about it. So first off, I went to the right identity using tangent with a minus, so I have tan of 225 degrees minus tan of 30 degrees over 1 plus tan of 225 degrees times 30 degrees, tan of 30 degrees. So basically, when we plug in our values, tangent of 225 is 1, tangent of 30 degrees is root 3 over 3, tangent of 225 is 1, and tangent of 30 degrees. So we get, putting these two fractions together, we get to here. So we have a complex fraction here. So when you do a complex fraction, how do you remove that 3 out of the denominator up here and the denominator down here? You do that by multiplying the top and the bottom of the fraction by 3. So it looks like that. Now when you do this, you have to remember that you have to distribute to both parts in the numerator and both parts in the denominator. So I have 3 times 1 is 3, and what happens when I multiply 3 times the fraction, root 3 over 3? Well, this is 3 over 1, this is root 3 over 3, so these 3's are going to cancel and just leave me with root 3. And by doing that, we got rid of that extra fraction in that complex fraction and turned it into a little more normal situation. So once you do that, you end up with this result. Now we learned in Algebra 2 we don't leave radicals in the denominator of the fraction, so we need to get it out. How do you do that when it's a binomial? You conjugate. So that means you multiply the bottom and the top by its conjugate, and the conjugate is the same binomial that only differs by a sign. So I'm going to multiply the bottom and the top of this fraction by 3 plus root 3. Now when you do that, when you multiply the bottom and the top by 3 minus root 3, because notice these are the same binomials, they only differ by the plus and the minus sign. So this is kind of like difference of squares on the bottom, and that's why we use it, so these middle terms will cancel. So if you need to FOIL the whole thing out, that's fine. If you remember that in this case you multiply the top, or the first terms, 3 times 3, and that gets you the 9. You don't have to do the O and the I step, and then you multiply the last terms. Root 3 times root 3 is root 9, which is 3, and don't forget it's minus. If you're afraid you'll forget that, then just FOIL that thing out. So now we're going to collect like terms, and that means we have a 9 plus 3 on top, which is 12, and then a negative 3 and another negative 3, so I have a negative 6 root 3. On the bottom, the negative 3 root 3 and the positive 3 root 3 are going to eliminate because they're opposites, so 9 minus 3 is 6. So now we just need to finish this out by simplifying that fraction. So there are a couple of ways you can think about it. I tend to prefer doing this because I find that that keeps me from making mistakes or forgetting to simplify something. So I split this back into its two fractions. 12/6 simplifies to 2. The 6 divided by 6 simplifies to 1, and you're just left with root 3. You could think about factoring out the 6 and simplifying with the denominator and then going from there. What I want you to be careful about is not going, oh, 12 divided by 6 is 2, so that's 2 minus 6 root 3. It's like they cancel with this first piece, so they don't think it applies to the second. This way keeps you from doing that. This way you might have to simplify one more time if you do it that way, because maybe whatever the denominator simplifies might still have something to simplify with one or the other. So this would be my recommendation, but if you're doing this comfortably and getting it right, I'm okay with that. So our final answer then is 2 minus root 3. So that's a little bit longer. There are a lot more things you had to think about in that problem. It's a little easier with sine and cosine because you don't have to deal and do all the fraction work. And finally, question 6. This one says write sine of 140 degrees, cosine of 50 degrees, plus cosine of 140 degrees, sine of 50 degrees as a single term. What that means is take this and apply it to the rules and figure out what the left-hand side was. So which identity should you use? Well, I looked at my identities and looked on the right-hand side till I found sine A, cosine B, cosine A, sine B, and that ends up being the A plus B rule. So that means A is 140, B is 50 degrees. So here's the identity that I'm using because this side matched up to this side, and I'm working my way backwards to get this together. So see, if I'm using this rule, that means A is 140 and then B is 50. So I can walk backwards to 140 plus 50. Now that I've done that, all I have to do is add it. So sine of 140 plus 50 is the sine of 190 degrees, and that is not a unit circle point, so that is your final answer. So most students kind of don't mind the sum and difference angles other than just learning the rules, but they're pretty straightforward. They're easy to work with. If you have a good grasp of your unit circle values and you get a good grasp of these rules, this is a pretty straightforward topic, so hopefully you won't have any trouble with that. Next time we'll be working on section 5.5, but out of section 5.5 we're going to work on the double angle identities. And so we'll have another set of identities next time. Thanks, guys.